Okay, you're live.
So this project is covering, what?
Introduce yourself.
Okay, well I was going to introduce this. So this project is going to be covering step boat hull mechanics. My name is Brandon Zelensky. I am a senior one at Kettering University. My personal interest in this project is that my family owns a powerboat, and we have a traditional style hull, and my entire life my family has always pointed out the other powerboats with stepped hulls, saying they're much more efficient, they move faster, they're better in every way, and I've always wondered what makes it that way.
My name is Dean Klebjian. I'm a senior 2 here at Kettering, studying mechanical engineering. My personal interest in this project was just kind of as a broad, better understanding of fluid dynamics. This is something that has always interested me, especially in the field of engineering. And so any opportunity to do physical testing using a wind tunnel, stuff like that, was something that I wanted to be a part of and just experience to have a better understanding for how fluid flows over different surfaces.
My name is Josh Goff. I'm a senior 1 mechanical engineer. I work in automation. My family does not own a boat. I do not watch boat racing. I didn't even really know what a stepped hull was before this, but I've always had a vested interest in problem solving, and it's ultimately why I'm becoming a mechanical engineer. And so when presented with the opportunity to figure out how can we make a boat faster and reduce drag, I quickly jumped on that.
So our goals for this project is to basically continue our learning experience outside of the classroom by incorporating the wind tunnel with by using the wind tunnel to collect data and results, and then using the equations we learned in class to further our knowledge. Our second goal is to design and perform testing on these boats to basically I'm losing the word. I don't know. Get results. I'm sorry. So a little bit of background for steps. They were initially invented around 1910. The first stepped hull was actually a boat similar to this, where it had 2 outboards, and they basically cut the boat in half and then raised the one side to reduce all the surface area. It was highly inefficient. It was very dangerous, but it did work. So they continued with that design until about 1980, where they started to actually think about the aerodynamics and design of the stepped hull. What would happen is the front of the boat would touch the water as well as the back, but nothing in between. So if any kind of left or right movement happened, the boat would radically veer off and it would flip over and kill everyone on the side. So what the stepped hull does, it decreases the surface area that is wetted by the water. It also creates low pressure zones in these steps, which will force air into the cavity, which will pick the boat up out of the water further, which will reduce drag and increase lift. It also, with increasing lift and reducing drag, will cause the boat to have a higher efficiency, which can make the boat go faster, also reducing emissions. So in our designing, this boat is related to a 38 Fountain Lightning. With the 38 Fountain Lightning, it is a common speedboat that normal people can buy. I use the dimensions for length and width to base our scale model off of. As you can see here, it has steps, which our boat also has steps in roughly the same location. I was able to use SolidWorks CAD software to design a few sketches and use a loft feature to loft the entire boat, mirror it, and then shell it, so we can actually print the boat. So our first design was this little guy. It was basically a proof of concept. It turned out well. Similar to other groups, the printers that we used had a 10 by 10 by 10 printing surface area. So we ended up having to cut this boat in half, but we added tabs on the side so we can put them together and secure them with super glue. We then sanded the surfaces down, and then I also used another cut extrude feature with a sketch to create our first steps. So we went into the wind tunnel lab with Ray Russ the first time. We showed him our boat, and he introduced us to the lift drag machine. And basically his only inclusion was, you're going to need a bigger boat. So we went along with this idea and basically increased the size of the boat, and then from there we inputted holes where our pressure taps would end up being. There are holes for a control pressure tap, which is in the top half, which stays the same. This control pressure tap will give us a control pressure which should be roughly the same. It'll also give us a good base pressure to go off of. And then we introduced 2 static pressure taps that we can actually get our data from. Along with that, we put in 2 more static pressure taps inside of the steps to show if we have a higher or lower pressure. This is the same as the standard hull. It is the exact same size and shape, just without the steps. The static pressure taps are in the exact same location. And then in the front half of the boat, we also included a stagnation pressure, so we are able to get correct data. And then we also designed a quick mount that the mount will mount up to the lift drag machine. We were able to do 2 different variations in angle. With the stepped hull, it should decrease the attack angle, which should decrease drag. And then all of this is 16th ID tubing. Found it in Amazon. It's pretty cheap, but it works.
So once we had our physical model, it was time to test our product. So we had 2 different products here. Ultimately, we'd like to test a full-size boat on the water, but we didn't really have the capability. So here we're trying to compare 2 different boats to see a relative change rather than an absolute change. So we're testing our normal hull and using that as a baseline to compare our data to the stepped hull. So why test a boat in the wind tunnel? Obviously, we'd rather be in a 40-foot power boat on the beach, getting a tan on, but we didn't have that quite available in our budget, so we quickly had to scale it. We also we didn't have access. We discussed with Ray Rust access to a water accelerator where we could actually test this boat in the water. So our next option was using the wind tunnel, and there were going to be a couple limitations in that because we're eliminating water from the equation, and we're taking an application where there are 2 different types of fluids, air and water, and turning it into just water. But since we are using a baseline of the regular hull, we are able to get a relative change rather than an absolute change. So before we even went into the wind tunnel, we had to set up a test matrix, and before we had to set up a test matrix, we had to figure out what we expected to see. And so after doing some research, we figured out that with our stepped boat hull, we should see a lower drag at higher speeds and a higher drag at lower speeds. This higher drag at lower speeds from our research is when the boat is not on plane, we are actually increasing the wetted surface area because there are no air pockets generating in this. And so from our submerged surfaces lecture in class, we are increasing the force by increasing the surface area. So there's going to be an inefficiency. We expect to see an inefficiency in the stepped hull at lower speeds, and so we knew that we had to test at least low and high speeds. We expect to see lift on the hull regardless of speed in the stepped hull comparatively to our baseline. And at our static pressure taps inside the hull, inside the steps, we should see a lower pressure comparatively to the static pressure taps outside of the steps because there should be air pockets here rather than where all our force is applied. So with that in mind, we created a testing matrix. We decided we had to change our tests between the regular hull and the stepped hull, and then we also opted to test at 2 different speeds with 2 different attack angles in mind. So this would be changing our boat on plane versus off plane, and then so that we could see the effect of the inefficiency of steps at lower speeds, and then we could see how it behaves at higher speeds. to keep things organized, since we accrued 8 tests with our testing matrix, we established a testing procedure so that we could not mess anything up. So first thing we had to do once we got into the wind tunnel was we had to make sure that our setup was correct to our tests. So this being the correct angle, we had to verify that we had the correct boat set up, the correct hull. We were going for the correct wind speed. We made sure to zero out all our lift and drag readings from the previous test. And then before even running the test, we ran at speed before recording any data to verify that nothing was too abrupt and everything was running smoothly. Once all of that was done, we established that we would record data and repeat the above steps for our 8 tests. So I've got a couple pictures here showing the routing of our static pressure taps in the wind tunnel. And then this is where they plug into the data acquisition machine, so right here. So we had 7 static pressure taps in this test. I have a video here of our stepped boat hull. We'll run. So this is our stepped boat hull running at 35 hertz on plane. So you can see how much the boat is shaking. This is one of the things, if we were to do the test again, we would have designed in a different mount so that we could try and remove this, this turbulent motion. But we were running the test at 75 miles an hour, so that's pretty realistic. We would have liked to go a little faster, but because of this motion, we didn't want to break the model. We wanted to collect data. So once we gathered all our data, we kind of sat down before going through and figuring out if our stepped hull is any better, and we came up with a list of limitations so that we could relate that to our actual test. So we're testing with air, not water, obviously. So that's going to have a substantial impact on our calculations. The rigidity amount, we are collecting data only at like a single point. So when we run the pressure taps, we are only seeing a single, not even a second of the pressure. And so if our mount is moving all over the place, we might see a sudden spike or a sudden decrease in our pressure. And so ideally, if we had more time, we would have liked to run these tests 10, 15, 20 times, and we could average out all of our numbers and get our outliers. But with our time limitations, we weren't able to do that. So we kept that in mind when we were coming to our conclusions. We also had an open bottom of the boat, as you can see. Ideally, we would have liked to have covered this all up because this is going to create a lot of turbulent flows, and this might affect our lift and drag numbers. However, this open bottom boat is consistent between the 2 tests, between our regular hull and our stepped hull. And so since we're not looking at absolute values and we're comparing between the stepped hull and the regular hull, it should not affect our conclusion. And obviously, we're scaling a 40, 45, 50-foot boat down to 30 inches, and we're scaling it in air and not water. And air does not scale as linearly as water does, and so we also had to keep that in mind when looking at our conclusions.